Welcome back, everybody, to the Python primer for student researchers. Today, we're going to look at fitting nonlinear data using the Python curve fit function from SciPy. So let's go ahead and import all of our libraries again. So I'm going to say from SciPy, import SciPy optimize, import curve fit, because that's the one we're going to be using. And then I'm also going to bring in my NumPy and my matplotlib. Make sure those work. Okay, so let's see how we can fit nonlinear data. And for this example, I'm just going to use an exponential, but you can do this with any set of data or any function that you can imagine. All right, so let me start by defining the function that I'm going to fit. And I'm just going to call this func for a name. And we're going to make this an exponential with 3 parameters. Our last fit had 2 parameters as a line, so this will be a 3-fit parameter, or a 3-parameter fit. And it's going to look like an exponential, which is a times np.exp minus b times x plus c. So this is an exponential curve, and that's what we're going to be using for our fit function. So let's go ahead and, just like we did last time, let's generate some data. So we're going to say x data is equal to linspace 0 to 4, and we're going to do 50 data points this time. And then my y data is going to be equal to the function. And we're going to put in some parameters just to generate this. Let's just say 2.5, 1.3, and 0.5. Okay, so those are A, B, and C, and I just kind of pick those because they look nice. And then we're going to create a distribution of normal data around that. So last time we did random data. This time we're going to do normally distributed random data. So I'm going to start by doing a random seed to my data. And then we're going to generate that random uncertainty with, rather than using random, we're going to use the normal function this time, but we're going to make it the size of my xdata.size. Okay, so that's just generating the uncertainties, and then I need to add that to my data. Plus y error. All right, so let's take a look at what that looks like. Plot.plot, x data, y data. And I've got, right, I need to say MP. And there we go. So that's, some randomly, it's random data associated with an exponential function. You can see it dropping off. So now we want to try and fit that function using our curve fit. All right, so we have our data, we have our function. So let's go ahead and do this. So we're going to say, again, parameters and covariance. And we're going to set that equal to curve fit. We're going to say x data, y data, and that's, and we need to put the function in there. So we're going to fit it to the function func, and we're going to do our x data and y data like that. We're then going to calculate our param errors by doing a square root of the diagonal of that covariance matrix. Like that. Okay, so that worked just fine. And we can go ahead and plot the results and see what we have here. So we're going to do a plt.plot, and we'll plot our x data versus our y data. And we're going to make this, we're going to actually, let's put these with error bars, right? Because we have error bars. So let's say the error, plot.error bar. And then we say y error here. And we'll format those to be dots. And let's go ahead and give that a label. make sure that worked. Okay, so there's our data there. Now let's go ahead and add our line. So we say plot dot plot. This will be our fit. We say x data. We look at our function and we say x data. And then I do this special notation where I say star parameters. And what that's doing is that's going to pass all of the values from parameters to that function. So that function takes 3 parameters up here. This parameter array has 3 values in it, and putting that star there just says send all 3 of those on there. And then let's make this a red line. So I do R like that. And then let's give it a label equals, we're going to call this the fit. Let's see what that gives us. Perfect. Look at that. All right, now this is not complete because we need to add some axes labels. So we're going to say x label. We'll call this x unitless, and plot.y label. Call this f of x arbitrary units. We've got to put our legend in. Plot.legend. And let's see what we have there. Oh, let's add our plot.show just to finalize that. There we go. Look at that. And why don't we add a title too? It'd be awesome. So plot.title. We can call that exponential fit. Boom. Check that out. That looks beautiful. And if we want to see what our datas are, we can just say print parameters. And we can say print parameters param errors. And that tells me that those are the values with the associated uncertainty. Those are not the same as these because we have uncertainty in the data, but they're pretty close. 2.8, 1.3, or 1.2 and 0.44. But you can see that those are the error bars associated with those uncertainties. All right, so that's how you do curve fitting to nonlinear data. Now, the other thing that you can do is you can bound the parameters that you're curve fitting to. So let's say, for example, that you have some data and you know that one of those parameters can't go any higher than, say, 2.5. Let's say this first one, the model that you have for your data can't go any higher than that. So what you can do here is in your parameters, in your curve fit, just come up here and type bounds, and then you're going to give it an array. You're going to give it 2 lists, the lower bounds and the upper bounds. So we say bounds, let's say 0, 0, 0. So it's going to start looking at 0, 0, 0 for A, B, and C. And then we're going to give it another list, which we're going to say the limit for A is 2.5. The limit for B, let's say, is 0.5. And the limit for C is 0.5, let's say. Let's make this 1.5. So this is going to do bounds for, it's going to make sure that the A value can't go any higher than 2.5, the B value can't go any higher than 1.3, and the C value can't go any higher than 0.5. And if I run that again, you'll see I get a different fit, and it's actually fixed this parameter to 2.5. And you can even, if you change these, say this one can't go higher than 1, the fit is not as good, but maybe there's some physical reason why these 2 parameters have to be 2.5 or 1, and there's some systematic bias in here that you don't want to fit to. So you can fix that with the bounds. And I want to point out that you can do this with any function. So depending on what your data are, all you have to do is change will allow you to fit to that function instead.